Okay, so good morning everyone. My name is Krzysztof Krawiec. I'm a professor here at the Institute of Computational Science of Poznań University of Technology. And this is my pleasure to moderate today's keynote, the second day of our event. I'm also happy to see that the after party yesterday hasn't entirely decimated the audience. Yeah, the attendance is actually pretty good. And without much ado, let me introduce our keynote speaker today. It's my pleasure and honor to introduce Dr. Mateusz Malinowski, who is currently a staff research scientist at DeepMind. And Dr. Malinowski, his career is, I would say, very international. He started his career in Poland, then he did his PhD in Germany, in Saarland University. His PhD received multiple awards, and currently Dr. Malinowski is working mostly in the area stretching, connecting computer vision, natural language understanding, and reinforcement learning. And his works have been cited multiple times. I've checked the number of citations. Google Scholar is in the order of, I think, 7,000 or more. And I must admit that I've been citing some papers by Mateusz in the past, because indeed some of his works, for instance, on graph neural networks, are quite fundamental and contributed importantly to the field. Then, without much ado, let me pass the mic to Mateusz, and the floor is yours.
Thank you very much for nice introduction. Today I'm going to talk about a few topics that I'm going to put under this umbrella term that I call training and inference at scale. So here's the plan for the next 1 hour. So I'm going to talk about modalities. So for instance, how to do faster inference by using half attention. This is especially important for networks like graph neural networks or transformer or relation networks. Then I will talk about how to use different modalities for self-supervised learning. Next I will introduce complex vision. So this is our new framework to speed up computations. And then finally, I hope that time will allow for it, I will talk about long video generation. So this is the project that, this is the most recent project, and the project that I will be working on in the next few months as well. Okay, so let's start from the first part of this talk, and this is about using multiple modalities for machine learning. So first of all, by multiple modalities, we often mean using language and vision. And why we are doing this? So first of all, we can use vision and language for question answering problem. And in particular, we can think that if people are, let's say, visually impaired, then they would like to understand what is going on in the scene. And by this, we can use different computer vision techniques, and then we can also use NLP techniques to answer questions that those people might have. Another possibility or another application for using language and vision, or even more modalities, is to have AI assistants that should interface with us not only by using language or speech or text, but also to use other modalities, crucially including vision. Language could also be used to steer reinforcement learning agents to achieve the goal. So here, for instance, I'm showing an example where we are giving different instructions to agent, and the agent has to move from one part of the city to another part of the city. And then finally, we could also use vision and language to disambiguate one modality. So here, for instance, I'm showing the example of underground station, and there is this sign way out. And of course, if you just use way out, literally, if you follow this instruction, you will turn left and then bump into the if you see vision and if you also understand, if you also have common sense, then you wouldn't do this. You would instead you would go into this tunnel. Okay, so that's about the introduction. And first, we are moving towards the following topic, which is speeding up inference of neural networks that requires a lot of computations, like for instance transformer. And we can do this by hard attention or selective attention. And here's a very nice experiment that is showing that selective attention is a part of our human visual system or our brain as well. Okay, cool. So you can see that some form of the selective attention, or something that I would call hard attention, is a part of our cognitive system. And there are some reasons why we are using this selective attention. And this is also something that I and a lot of other researchers also try to use in neural networks. And in terms of the neural networks, you can also think that if you start using attention, or hard attention, or even soft attention, then we can deal with longer memories, basically. There's, the problem of the gradient vanishing issue is less emphasized. There's also a possibility to exceed the limitations of global representation, because then basically we can use self-attention to query what are the points that are important for the network to focus on. And here I'm also showing very simplified, in simplified terms, how this hard attention or soft attention could work. So let's say that we have the scene, and then we have our question, how many rectangles are there? And this scene is quite complex. However, if you have some kind of processing mechanism that could, let's say, only select the red triangles, then the answering to this question, which is a counting question, would be far easier. So there are two variants of the attention that are commonly used in machine learning. The first variant is soft attention, and this is the most popular. Why? Because it's differentiable. You can easily backpropagate, you can optimize your neural network end-to-end. It also gives a statistical efficiency, because the network can basically focus on the parts that are important for the inference. The problem is that there are no really computational benefits. The network has to still attend over all the received input tokens. And this contrasts with hard attention. Hard attention selects only part of the input that is important for the inference, for the reasoning. And it has this benefit of not only having statistical efficiency, but also computational efficiency. Now neural network doesn't have to only attend on, doesn't have to attend over all the input tokens. It only attends to input tokens that are important to the inference. The problem, however, is non-differentiable. It's optimization problem that involves discrete optimization problem inside. Modern networks can be, especially like transformer or relation network, can be seen as a fully graph-connected networks, right? So for instance, you can imagine that we have a scene and then we have objects in the scene, and what transformers are doing, they are building the powers, connections between all the possible objects. And now you can see that this graph, which is a foundation of the self-attention, has one problem. It's a computational problem. It requires n-square interactions between different parts of the input. And the question is how we can speed it up. And here, one such possibility is to use hard attention. So for instance, we could still use self-attention, but self-attention on much smaller number of the input tokens, on the input tokens that are relevant for the task. So here, for instance, at the beginning we were using n-square computations, and now we are still using quadratic computations, but with respect to k, and k is hopefully much smaller number. Of course, there are other ways of achieving similar results. For instance, we can also use cross-attention to project high number of the input tokens into smaller number of the input tokens. And this is, for instance, done by with receiver, which is one of the computationally efficient competitors of transformer. Yeah, in our work we focus on the hard attention, and we noticed that we could use norms of the features to understand what part of the image are important with respect to the question. And then we can basically cut or crop only those parts of the image that are important for the inference. During training, because this process is non-differentiable, we use straight-through estimator. So straight-through estimator is the way how you can, one of possible ways how you can deal with non-differentiable functions inside your neural network. And then we applied this technique to Clever dataset. So Clever is a visual question answering dataset with synthetic images containing different objects with different shapes, with different colors, attributes, and quite involved, quite complex questions. Like for instance this one. What is the color of the cube to the left of the big metallic sphere? Yeah, it's not so easy to answer this question, even bias. Nonetheless, by using hard attention relation network, we can gain more computational speed, and therefore we can also use a bigger neural network. And because we can use the bigger neural network, then we can also achieve better results. So here there's estimated human performance at the bottom, which is about 92%. Relation network is our first work that was dealing with this kind of problem, and it achieved 95% accuracy. And finally, with hard attention, we can run much larger relation network, and we can achieve even higher accuracy number. We can also apply the same technique for realistic images, and here's also one such example that you can see. The question is, are these lions? So in this data set, there are also, as you can see, typos, but neural networks has to also deal with uncertainty or noisy textual inputs as well. So that's a part of the game, I would say. Yeah, and this is good not only for the computational speed or statistical efficiency, but also to some extent to have some form of the introspective capabilities, right? So you can introspect, you can see if those answers and together with the attention maps make sense. Okay, so that was the first project, and now I want to talk a bit about self-supervised learning. So commonly used framework in machine learning is supervised learning. In supervised learning, you have a bunch of inputs, image data, like for instance, here we have some scenes with cars and so on. Then we give those inputs to people, and people give annotations of those inputs. So in this example, it's a semantic segmentation. So the idea is that people will put colors on different parts of this image, and each color is corresponding to some category, like for instance, vegetation, sidewalk, vehicle, fence, and so on. It's a very popular framework in machine learning, and it's also very successful. However, it has a few problems. So the first is that it's time-consuming to collect such annotations. Second is that it's also quite expensive to collect all these annotations. So in all, it doesn't really scale up. So it's a process that has some limitations in the form of scalability. So instead of using supervised learning with human annotation, there's also another approach for achieving something similar, which is called self-supervised learning. So in self-supervised learning, the idea is that perhaps by transforming input data by some transformation function, we can get the supervision signal, but at the same time, we don't have to ask annotators for doing this. I will give a few examples here to make it a bit more concrete. So let's say that we have this image of a cat, and now what we can do is that we can randomly sample some part of this image, and next we can also collect a few patches that are close to this central patch. And now we can ask, we can label them, so we can say 1, 2, 3, 4, etc. And now the question is if this relationship between this patch and this patch is at which side? Is it like number 1, number 2, number 3, or something else? So what does it give us? This gives us a label, right? So now we don't have to ask human annotators. We can do this fully automatically, this kind of annotation process. And at the same time, we enforce the neural network to understand something about the spatial relationship between different parts of the image. There are other possibilities for self-supervised learning. Another possibility is to use polarization. So for instance, we have RGB colorful images. We can transform them into gray scale images, and then we can ask neural network to colorize them again. For this, we don't have to ask human annotators to annotate those images. This can be done fully automatically, so this approach scales up very well. And at the same time, we enforce the neural network to understand something about the objects, about the categories, about the colors, and so on. So this is one of the architectures that is doing this polarization. It's a kind of unit architecture, but for this it's not like super relevant. At the beginning, self-supervised approaches had much lower quality than supervised approaches, and here there's such an example. So the supervised approach at that time, state of the art, was giving 87% accuracy. Colorization was giving only 55% accuracy, but it is still a miracle that it was working because it's a very simple idea. And later, self-supervised learning approaches became, in terms of the accuracy, they become closer and closer to those supervised learning approaches. Okay, so this is the universal recipe for self-supervised learning framework. We have a data set of a lot of inputs like images. Then we have some pretext tasks. So pretext tasks can be colorization, or it can be basically cropping those patches randomly that I showed to you. Then we can use this pretext task to do retraining of the neural network. And then we can either fine-tune the network on the downstream task, or we can probe the network on the downstream task. So probing means that we put a single linear layer on top of the pre-trained network, and then we see what is the accuracy of that network on the downstream task. Why there's only a single layer? It is because we want to we want to benchmark the representation, the learned representation of this neural network, right? So the idea is that if the network understands well images, then just linear layer should be sufficient to solve the downstream task. Okay, but the world is multimodal, right? So it's not only about images, it's also about a lot of other stuff, about other modalities. So here I'm depicting a concept of a dog. And with the concept of a dog, there is also associated, or we often associate a category, dog. There's also an image of a dog. There could be also a video of the dog. And there can also be a sound of a barking dog. And all those different views, all those different, let's say, modalities, they are projection of the real dog, right, into some, let's say, different conceptual spaces. And each such modality is telling something different about the initial concept, about the real dog. So now the question is if we can use this in the self-supervised learning framework. And sometimes I like to depict this in this form. So the whole concept is this, let's say, the rectangle that is fully filled with those smaller rectangles. But we don't have necessarily direct access to the full concept. Instead, we, through our sensory inputs like vision or text or by hearing and so on, we have only access to this concept through those sensory inputs through different modalities. So basically there are different modalities, and all of them together are saying something interesting about the real object, which is a dog in this case. But each one individually is insufficient. So why not to use those different modalities or different views of the same concept and use one modality to predict another modality, right? So for instance here we want to we take the input modality like this one, and then we want to which is coming from the concept of a dog, and then we want to predict what that modality, what that input give in different view, in different modality. So you can imagine that, let's say, the modality 1 is image, and then modality 2 is a text. So basically, it's just classification. So let's describe the image using text. But this modality 2 can be audio, or it can also be another image of the same dog. And we can also do this with multiple modalities. We don't have to only restrict ourselves to only 2 modalities. Yeah, and we did some experiments in the self-supervised learning, using self-supervised learning framework and using different modalities. And we developed an architecture that we call Brave. This Brave architecture works conceptually in the way that I already described. So basically the idea is to predict those 2 modalities, right? So to take as an input one modality, predict another modality. Here, those 2 modalities are basically different, the same video of the same concept, but those videos are different in the way that those are very short videos that are high resolution, and here there are longer videos, 5-10 seconds of the same action, but with the low resolution. And the idea is to basically take this as an input and predict this as the output, or take this as an input and predict this as an output. Because those inputs and outputs, like those videos, are high dimensional, so the predictions are very difficult. So it's very difficult to predict 10 seconds of the video. So instead of doing predictions in the pixel space, instead we do predictions in the feature space, or in the latent space. So latent space are much compact representation of the inputs, and then we are trying to use one modality, project them into some latent space, and then use this latent space to predict a view, another view, or another modality, but also in the latent space. We can use other modalities. We don't have to use the pixel space. We can use, let's say, semantic segmentation mask, or we can use flow. We can also use audio, and we can basically try to match between those two different modalities, so two different views of the same input, of the same concept. And by doing this, we achieve, I would say, pretty strong results. Here I'm showing only a single data set, but we have experimented with different various data sets. As the fully supervised learning approach is giving 98% accuracy. Our approach is giving 90% accuracy, but if we also use flow, we are getting slightly boosting the performance, and if we use flow and audio, we get even better performance. And this is in terms of the probing, not in terms of the fine-tuning. With the fine-tuning, we get higher results. So in some sense, it's cool because we can use the input data. We don't have to use labels anymore. We can use only input data to learn the representation, and then hopefully later on we can solve a downstream task. We can also use different modalities like vision and language to learn the representation, a better representation, even though that we are not interested in one of such modalities. So for instance, we want to translate between two different words or between two different texts. So we have two different languages. We have two languages, like let's say English, and then we have French. And with each such language, we have associated videos. The task here is to translate between those two languages. So we don't need videos at the end, but perhaps we could use videos in training to achieve better results. And what is intuition behind that? The intuition is that if we have two different languages, and we are interested in the concept of egg, so let's say that we have this language and we have egg, and then we have if, which is a French version of the egg, then those words seems to be quite different. But the concepts are, like visual concepts, are more universal, right? So there is the same breaking egg here in English, and if you go to your French friends, they would also do basically the same with the eggs. So the concept is the same, the video is the same, visual input is the same, but words that are describing those videos are obviously different. And here we propose such architecture that is basically iterating over forth and back between different languages, and with different videos that are associated with this with those languages. At test time, we don't care about videos, so we can drop them, and then we can use basically the ADAPT layer, which translates between two different languages. And this is done in an unsupervised way. We don't have to have a mapping between words between two different languages. And here are our results. So MUF is our approach, which uses videos for training, and MUSE is another approach that doesn't use visual data, and it's an unsupervised learning approach to translate between words between two different languages. It's a very cool work actually, because it shows that there's a possibility to translate between two different languages, between two different words, by just doing orthogonal mapping between the feature map of one word and another word, which gives this cute geometrical interpretation that basically two languages can be seen as rotation between each other, right? So let's say that English is a rotation of the French language in this feature space. So here we can see that in translation between two languages like English and French, our network is giving a bit better inputs over the Muse, but the improvement is not that big. It's not that big because those languages, like English and French languages, are close to each other. But if we use more dissimilar languages, like for instance English language and Korean language, then the boost in the performance between Muse and ours Muse is much larger. So we can conclude from this that if languages are different, then actually this rotation, this geometrical interpretation that one language is rotation of another language doesn't hold anymore. And we need some stronger assumptions. We have to work with under stronger assumptions, and here we can use basically videos or images or visual input in general to achieve this unsupervised mapping. So that finishes the first part, which is about modalities. And now I'd like to proceed to newer work that I've been working with Olivia Walls and a few other people at DeepMind. And this is a new framework for more efficient video understanding or video processing. Okay, so first let's think about video understanding task and how it works. So basically in the video understanding task we have clips, and then we want to classify those clips. So you can imagine that it's kind of ImageNet equivalent, but instead of images we have videos, and instead of object categories we have actions. The problem here is that those videos, those clips are very short. They are limited often to a few seconds, sometimes maybe a few minutes, but that's all. However, what we would like to do is to work on much longer videos. Like for instance this one. It's a 3 hours long video. It's also an egocentric video. And it has a lot of continuity, but it also has, it's basically much longer than the videos that you can see on the left side. However, those videos are also much more realistic to some extent, right? Because if I think, let's say, about myself, then, and I spent here almost already 40 years, then I would say that in terms of the videos, I watched something like almost 40 years of long video, right? So now the question is if neural networks can also spend a life like myself, and they can experience years and years of such continual videos. There are, however, many challenges in the long video understanding. So the first such challenge is that a sync video, which last hour, corresponds to 90,000 images. This means that the volume is huge, and even sample this input data, if you have a distributed system, is difficult. And process such long data with neural networks is also difficult. And this is only by the sheer size of the input data. It's really, really huge. Another issue, another challenge, is that we don't have publicly available benchmarks on this task. We have a lot of benchmarks in the video understanding community to deal with short videos, but not for the long videos. And you can imagine why this is happening. It's because it's difficult to collect, it's difficult to annotate, it's difficult to process those data. So there are many challenges. And as it also turns out in our project, is that the currently available computer vision or video understanding methodology is definitely way suboptimal for dealing with longer videos. Okay, but now the question is, instead of working with in the pixel space, that is huge in this case, so in this case it's like 90,000 frames, that corresponds to 1 hour video in resolution 256 to 256, which is again not that high resolution, and this becomes even more problematic if we start dealing with high resolution. So instead of dealing with this input data, what can we do to compress this input data to much smaller tensor? And if we could compress this data input tensor to something like 316 by 60, we would we could speed up the whole process. The sampling becomes easier. We can perhaps even put 1 hour-long video in a single device, in GPU or TPU, because it fits the memory. At the same time, we also want to have representation that is universal. So for instance, we can start thinking, okay, wait a minute, we can take ImageNet features, and then the ImageNet features would compress this input into 300 vectors, right? The problem is that those ImageNet features are not generic enough. They might not work, for instance, for the generation. So if you know state diffusion, they're using the latent space, but they're not using ImageNet features. From the ImageNet features, it will be very difficult to generate them, I think. Okay, so this is our currently used standard video pipeline. In the video pipeline, we have data that are compressed videos, and we often use either JPEG or MPG compression to store those data. Then we sample those data, we decompress them using JPEG or MPEG decompression. We apply some augmentations. So for instance, here there's a cropping and there's some kind of rotation. Why we are doing this? We are doing this because we want to make our neural networks to be more robust under some changes of the input data. And then we run a downstream model, let's say a video classification network that is giving the answer. Okay, the first change in this pipeline is that we train a neural network that can replace JPEG and MPG compression. And why we are doing this? Because JPEG and MPG compression is working quite well in the lower compression ratios, but in higher compression ratios you can see that JPEG and MPG compression is not working that well anymore. Right? So this is about 100 compression ratio, and you can see that there are a lot of artifacts. In contrast, our neural network codec can compress at even higher compression ratio with much fewer artifacts. Right? So if you compare those three videos, you can clearly see that these results are much better than MPG compression and JPEG compression. And this is very important because in the long video understanding, we care about very aggressive compression, right? Because you want to really squeeze as much as possible from input data into those smaller tensors to feed them into memory and so on. Okay, so now we have the first replacement of the standard visual pipeline, where we replace the JPEG codecs with our neural codecs. So we take the videos, we put them into some data, we compress them using neural codecs, then the codes we put into some data storage, and then we decompress them, and then run a downstream network on top of it. The problem is that okay, so there are benefits that we improve the memory storage. We can put more inputs into our dataset. But the problem is that the decompression is very slow. And decompression using neural networks is much, much slower than decompression using MPG or JPEG. And the reason is that we have to revert the latent space using quite beefy codec. Another problem is that it's still expensive to put this in device memory, and we also have to sacrifice the speed. So we are losing all the benefits of the compression by doing the compression. Right? We not only care about the storage data, but we also care about in-device memory. So what if we could just skip this step and instead train a downstream network directly on the compressed representation in the compressed data. This would give not only improved memory storage like before, but we also can avoid costly decompression step, and we can also put all this data in the device memory on GPU or TPU. So here's a new or revised pipeline. So we first learn a compressor, and then we use this neural compressor to compress input data into compressed codes, put them into the data storage. Then we use learn augmenter that is acting on the on this compressed representation. And we need this because we also want to have augmentations. And augmentations normally, typically, are defined in the pixel space. And then finally, we use a downstream network that does something with those codes, like group classification and so on. Okay, so let's maybe zoom into the first part of this pipeline, which is naming the compressor. And here I'm showing again the results at a very high compression ratio, which is 756 times compression ratio. It's very aggressive compression ratio. You can see that there are some artifacts, like things are becoming more blurry. There are also some ways to improve the blurriness in terms of adding more high frequencies. But this is something that we didn't deal in this paper, in this one. Crucially for us, we can see that the constructions are still quite faithful to the input data. Okay, so now the question is what I mean exactly by those codes, compressed representation, and so on. So for that we use VQVE, and VQVE, you can think that it's an encoder-decoder architecture that is taking the input image and is compressing into some latent representation. I will talk about this in a few seconds. And then it's taking this compressed representation and can decode into the image. The compressed representation here are basically discrete codes. So you can think that there is something like embedding space that are describing, and this is constant, so basically this is universal for all the image data. And now, instead of representing input data, images, in the form of such latent vectors, we represent those data in the form of indices to those vectors. So for instance, number 1 corresponds to this, number 3 corresponds to this, and so on. The whole network can be trained end-to-end, and because there's a discrete state here, like with the hypertension, we use similar mechanisms, which is called straight rule, to deal with non-differentiability in the whole pipeline. And thanks to this, we can train the network end-to-end. So now, when we have this representation, this bottleneck, we can throw away the input images, and instead of dealing with input images, we can work with those indices basically. We can store them, right? So we can remove those data, we can store only this data. And then if we want to decompress data, then we have to use those indices to take features, and then we use decoder to decode those features into the images. Please note that this scales as the input data, so we have as many such matrices as the input data. But this one, which is a set of high-dimensional latent vectors, is fixed. So it's independent of the size of the input data. And this is very cool property here. And by this, we can have basically a very efficient way of compressing this stuff. Here I'm showing the original VQV that was operating on the images, but we can extend this VQV into videos by either using 3D convolutional neural networks instead of 2D convolutional neural networks, or you can use space plus time convolutional neural networks. So basically, you can use 2D convolutional neural networks that are followed by 1D temporal convolutional neural networks. Okay, so we know how to compress data and how to put them into the data storage by using those indices. But another question is how we can apply augmentations, because those augmentations, like typical augmentations in the video pipelines or in computer vision in general, they are defined in the pixel space, not in the compressed or latent space. So what we do is that we actually try to learn not only a compressor, but also augmentor. So augmentor is a small neural network, and I emphasize here small because the idea is that we don't want to sacrifice the speed. Right? So we did these painful steps of removing the compressor, decoder, and one of the motivation for this is that it's an expensive process. So here we want to have augmentation network that is doing augmentations, and this network has to be sufficiently small so that the speed is quite high. And now what we can do is that we can take the input data, then we can use some handcrafted transformations. So for instance, a cropping, you definitely have a lot of functions that can do this. It's easy transformation. But then we train a neural network that is regressing to this transformation. Right? So we have the input, we compress the input into the codes, then we have another neural network that is operating on the codes, is giving some output, and then we use a magic loss, which can be L1 norm loss or L2 norm loss, that is giving the score of the error between the predictions of the augmentor and the handcrafted transformation. So mathematically this can be written this way. So C is our compressor, S is the input signal, capital A is the handcrafted transformation, small a is our neural network that is supposed to mimic the transformation, and C minus 1 is decoder, so it's decompressor. Right? So we take the input signal, we compress, we use a neural network A to do transformation of the latent. Next we take the decompressor or decoder, revert this into the pixel space, and then we match if this is the same as if we didn't do this complex kind of stuff and instead just apply the transformation directly on the input data. By some rewriting, you can also see that this is the basic definition of equivalence. So by doing all this kind of stuff, we want to learn equivalent model. And here we also show that this augmentor can be quite universal. We don't have to do with simpler transformations like copying that I showed before, but we can also change the brightness, we can do crop, we can do flips, we can also do some kind of rotation. Yeah, I think that this is flip, so this is flip and this is crop. And then we can even rotate. Crucially, here I'm showing everything in the pixel space, but I'm showing in the pixel space only for your convenience or for the debugging. We don't have to decompress this into the pixel space. We can do all these transformations in the compressed latent space. So that's the part of this framework. And then we evaluated this framework by retraining the codec on 2 different data sets, and then training a downstream network using those latent representation, this compression, on 2 different data sets, coin and kinetic 600. This shows that the approach is generic enough. On kinetic 600, we can see that there is a small drop in the performance. If you use the compressed representation, so 30 means 3 times compression, 475 means 475 times compression ratio, and 1 means no compression. It's basically the original network that is dealing with pixel space. So there is some small drop in the performance, but again, the whole purpose of this background is not to solve the existing problems, it's to solve problems that do not necessarily, they do exist, but we don't have benchmarks yet, right? So it's we developed this whole pipeline to deal with very long videos, not with short kinetic 600 videos. It's only to validate the approach on the existing data sets. We did the same with the current. So here, actually, with some small compression, we got a bit better performance than in the original RGB space. But again, this is mostly to validate the approach, not the task that we are super interested in solving. We can also see the reconstructions at different compression ratios using 3 different metrics, PSNR, SSAM, and mean average error. The smaller the better in this column, the higher the better in this column. So we can see that JPEG is pretty good if we are using small compression ratio, but it deteriorates quickly if we are using higher compression ratio. The same with MPG, and our newer compression is definitely far better than those two compression mechanisms at higher compression ratios. Okay, but at the end of the day, we wanted to process long videos, like for instance, video like this one, like 3 hour long videos. So what we did is that we collected data and we created a very simple task that is inspired by continual learning, and it works the following way. We have a video. The video is chopped into 5-second clips. The network observes parts of the video, and then each time, after each such clip, we are giving the query. And the query is simple. It's a question if this clip has been observed, so it's part of this part of the data, or it has not been observed yet, so this is part of this. We use the compression that I described before to compress everything efficiently. And we use a neural network that has some access to the memory. It also has have its core and is doing predictions. So prediction is a binary classification problem. It's basically the question if query has been observed or not. And at least for the 50 minutes long video, we got about 99% accuracy, which validates our pattern. And here we have also open source this framework if you are interested in. Okay, so this brings me to the last session, last part of this talk. And since I have about 3 minutes, it will be a very compressed topic. And it's 30 seconds video generation. And here in this work, first we were dealing with the problem if you can cast all the vision problem task using generative efforts. So we want to generate detection, rectangles, or semantic segmentations, or depth. And here I can say that to some extent we can do this, to some extent we are successful. In some cases like novel view synthesis and video prediction, at that time we were state of the art. But I'm not going to talk about the architecture, instead I'm going to talk about some of the results. So here, for instance, we conditioned on the 5 frames, and then we wanted to predict 20 consecutive frames based on the first 5 frames. We did something similar with this dataset, RobotNet dataset, which has the arm of the robot, and then we only conditioned 2 frames, and next we predicted 10 frames. We also use the same architecture to do the novel view synthesis. So we wanted, based on the input data, we wanted to predict different views. And for instance, here you can also see that if we use this only a single view, then this is what we can predict. We can definitely see some errors, like for instance, there's latency here. But if we put 2 views, then some of those errors disappear and it works better. We also generated, and I think that that time it was the first generation of 30 seconds long video using natural dataset with the following hierarchical approach. So we condition on the input image, which is this image. Then we predict consecutive images at low frame rate. Right? So for instance, if you are using, in this case, we are using 1 FPS. So we take so we predict the image after 1 second, after 2 seconds, and after 3 seconds. And next we use an interpolation network that is trying to take 2 neighboring images. So for instance, it takes this image, and next, based on those 2 images, condition to those images is trying to interpolate between those 2 images. And thanks to this, we get we can condition on a bunch of different images, and then we can generate first images at a very low frame rate. And this is cool because it's a very scalable approach, since we are not dealing with a lot of data. We are dealing only sparse data, sparse in terms of the time. But then we can use the neighboring frames to just interpolate between those two. And often those extrapolation, those prediction, is a much more difficult process than the interpolation. So this step is often much simpler than this step. In terms of the spatial resolution, the resolution is pretty small, but again, this can be upsampled quite easily. And some of those results are really cool. Like this one, for instance, here the network can basically learn to rotate, and it can consistently fill the missing details. Okay, so that's all. And I think that I almost squeezed everything in time. Yeah, thank you very much.
Thank you. Dr. Malinowski for this very interesting talk. I expect there might be quite many questions from the audience.
Hey, thanks so much, Mateusz. This was a great talk. I have a question regarding video generation. How do you know that a video generation method is good? Which metrics do you use?
I will disappoint you. I use my eyes. So we have some automatic measures, but actually they are not particularly good. To some extent you can, if you are, okay, so for instance you can use FID scores that are adapted to videos. So those are, let's say, population-based kind of scores. You can use them if you are testing models from the same family. So for instance, if you are changing the hyperparameters of the same model, then this might work. I'm not saying that it's working super well, but it might work. You might basically use the scores to select the best hyperparameter. But if you are testing different models, and each model has different the idiosyncrasies, then this metric is not that good metric. I've seen some examples where the difference in FID score were quite significant, but the results were insignificantly different. And sometimes I also have seen that there is a small difference in the metric, and actually the results are much worse. So at the end of the day, you probably need human evaluation. And as an intermediate step, you probably have to just look at those videos on your own. Yeah, it would be cool to have some automatic metric. Maybe we can do some self-supervised learning to develop such metric.
Thank you. And another question? Oh, there's one.
I've got a question about this learned augmentation, this decompressed space. Because I really like the idea, but I'm just curious about if this augmentation are conditional based on maybe, I mean that, let's imagine you've got the rotation augmentation, we can condition it based on some angle, like 40 degrees, 70 degrees, and let's move maybe forward. Did you learn the single augment model to handle all kind of augmentation, or there was a separate model for each type of the augmentation?
Yeah. So ideally, I would prefer to have just a single augmenter that is doing all the possible augmentations that you can imagine. But in this particular work, we learn different augmenters for different types of augmentations, but each such network is conditional on the arguments that are typical for the type of the augmentation. So for instance, in this case that you mentioned about rotation and the angle, we condition the network on the angle. And if we are using, let's say, crop, then we condition the bounding box, and bounding box is giving the coordinates of the crop. But ideally, I would also like to condition on the type of the augmentation. We did some experiments like that, but they were less successful than having a separate network for each augmentation. So, thank you.
Thank you. I think we still have time for perhaps one question, even though we run into the coffee break. There are two questions here.
Yes, so can I? Thanks. So I'm also interested in this part where you showed that you've learned a compressor, then for example the augmenter, and then some downstream task. So did you freeze the learned parts?
Yeah. Each part is trained independently. This also brings another interesting question. If there's a possibility to train augmentor that is actually specific for the task, right? So if you have some downstream task and you care only about this task, then perhaps you can find a better augmentation for it. In our case, we wanted to be as general as possible, and always there's an issue that if you train this kind of stuff on the downstream task, it will be too specific to the downstream task, so you might lose the generality. But if you are very keen to solve one particular task, there should be possibility to basically have end-to-end pipeline that is training the augmentor and the downstream classifier. And I think that this could be cool. We didn't do those experiments, but it would be cool to use the same framework, let's say, for self-supervised learning, because then you can really do this at the scale, right? So I showed those results on the kinetics and current, but I also mentioned that this is not really the best task for it, right? Better task is to deal with very long videos, and such benchmarks do not exist, so that's why I show our own data set. Or you can also use this at self-supervised learning if you really want to scale up this approach massively. So if you want to, let's say, learn from audio to videos or something like that, then probably you also need to think about efficiency.
And do you think like further fine-tuning the entire pipeline would actually make any sense? Or do you expect it to improve the performance?
It's hard to say because I think that it also depends on the amount of training data and diversity of the training data, because there is always the problem that if you train the whole pipeline, then things become very adapted to your dancing task, which is okay, but the problem is that it might also adapt to your training sample from the downstream task, which means it will overfit, and there's this risk of overfitting. But I believe that if you have sufficiently a lot of, and especially diverse data, then this should prevent from overfitting. It might also be interesting to see this, and it would be, personally would be also curious to see if we can learn augmentations that are maybe not even human interpretable, or maybe they are human interpretable, but they are not defined by the currently used handcrafted transformations, right? Because here we were just explicitly wanted to mimic the existing handcrafted transformations, but maybe we can go beyond that.
Thank you. So even though we still had some other questions from the audience, I think quite many of us may deserve a sip of coffee. I talked to Dr. Malinowski, and he told me that he should be available today for most of the day. So please don't hesitate to approach him in this coffee break or next coffee breaks. I can assure you that he still speaks Polish, right? So that's another option. So let's thank again our speaker for this excellent.